Okay, so here's just a little short intro video for the labs. So we're going to look at 3 different collision scenarios. So we're going to start with the one that most closely represents a perfectly elastic collision. So we're going to have 2 carts. We're going to have one of the carts stationary. So let me make some carts here. So I need 6 of these things. So we're gonna call this cart 1 and this cart 2. Cart 1 is the one that's going to be moving. We'll give that some initial velocity, and the cart will come along. It will hit the other cart, and we're going to have what we'll call a perfectly elastic collision. So they actually will not touch each other. We'll use the carts with the magnets in them, so they'll approach each other. They'll be repelled and then they'll bounce back, so there'll be no contact between the carts. The next one will have the springs that we've always had pop out and wonder why they're there. Well, the springs in the carts are to give you somewhat of an elastic collision where they touch each other, so that they will come to each other. The spring plungers will compress and then they'll bounce off, but because of friction it won't be perfectly elastic, but they will come in and then bounce back. Actually, what will most likely happen is this one will come along and this one will remain stationary, and then that one will move. The same thing applies up here. What most likely will happen is it'll actually come towards the other one, and then the other one will be pushed to the right, and this one will remain stationary. That happens when the 2 carts have the same masses, which will be pretty close to this correct. And for each of these 3 scenarios, we're going to measure the mass of the carts. And what we'll have is we'll have velocity. We're going to measure velocity for the 2 carts. Now for the 2 elastic collisions, the perfectly elastic collision and then the other one, what's going to happen is that the initial cart 2 will initially be stationary, so we'll have a 0 velocity. Cart 1 will have some velocity, positive velocity, and then there'll be this interaction where this one will go probably close to 0, and then the other one will go to about the same velocity. Now there'll actually be a slight decrease in velocity here because we have friction. And this one looks very similar. And then the last one, this is the inelastic collision. This is where the cart comes and it sticks to the other one with the Velcro, and then they move as a unit like that. That's the one will be looking different. What will happen is you'll still have cart 2 stationary, and cart 1 will be coming along, and then they will both slow down. Because they're about the same mass, they'll slow down to about half the original speed, and then they'll move together as one, whereas these separate when we have the elastic collisions. And what we'll do is we'll look at, we're not going to look at it in real time, but we'll do it in the lab, and we're going to look at momentum, total momentum, and total kinetic energy. So this will be momentum, this will be time, this will be kinetic energy versus time. Now the momentum will end up being going downhill here. Oops, wrong button. Because of friction. But somewhere in here is the collision. You know, the collision maybe happens over a short period of time. And what we should see is that we don't see any big changes in momentum as we go through the collision, because we have conservation of momentum before and after, but also during the collision, because there is no external forces applied except for the friction, which should be fairly constant. Now, as far as the kinetic energy is concerned, what we'd have is kind of this baseline. If no collision happened, but what we'll see is during the collision, the kinetic energy for the first two cases will drop off and then it'll bounce back. And what's happening here is where the energy is stored. And the energy will be stored inside the magnetic field. This is actually what the one will look like with the magnets. What we'll see with the case of the actual springs, it'll also have this dip where it's the energy stored in the springs, but instead of coming back to the original value that we would expect if there was no collision, we'll see it drops off, and this is the energy lost due to the imperfect collision. Whereas for the final scenario, the one with the inelastic collision, the one that happens here, what you see is you'll see that the kinetic energy drops off, but there's really never any energy stored. So it'll be more like just drops off almost like that. So there's no dip. This dip here is due to the springs, storage energy in the spring. Here we just lose energy as the two things stick together with the Velcro. And we'll do those looking at the momentum and the kinetic energy. We'll do that later using Excel. So we're just trying to observe what's happening, what kind of collisions they are, measure the velocities, measure the masses, because we need the mass for momentum. Momentum is mass times velocity, and kinetic energy is 1/2 mass times velocity squared. So if we have mass and velocity, then we should be able to do a pretty good job of calculating the momentum.